Thank you very much. So last time I was trying to tell you about how people can describe this altometric that's already featured in Martin Speight's talk today. So he was explaining how you get this localization working, the so-called Strawn-Stammel's localization. So I'm not really explaining that now. I'm just going to, refer you to Martin's lecture. So I'm going to complement that by just saying, explaining other ways of writing down this altometric on the moduli space of vortices. Okay, so another process, another viewpoint is to go via universal objects and fiber integration. Okay, so universal objects are, so there's going to be something that I will call a universal connection. Okay, so the moduli space is a space of connections, pairs, connections, and sections of bundles, which are identified under these gauge transformations. So here we have some kind of master pair that contains all the information about all the possible connections, all the pairs connection sections. Okay, so this is how it works. So we know that we start with this sigma, this Riemann surface. So the space where the vortex is defined, I told you that in my lectures it's going to be always a compact Riemann surface. So it has a complex structure which I call J sigma. So this induces on the moduli space, which I said in this case of line bundles, identifies with the symmetric product of the surface D times. So this is actually complex manifold of dimension D, and it has its own complex structure, which I said is actually easy to describe from this one. Okay, there's other parts of the geometry of this space which is hard to describe. This is basically my task now, but this is easy. So this is a complex manifold. So the most concrete example of a moduli space of vortices. Okay, and now so here we look at, so it starts in a way which is kind of almost trivial. We look at this product, the moduli space times the surface, okay? So this has two projections, so the moduli space into the surface. We're going to use both of them. So the map to sigma, I'm going to call P, P, okay? And now the thing that is important is that there's going to be a divisor here, there, which is going to be, I'm going to call discriminant locus. Okay, so if you like, it's a subvariety of complex codimension 1. Okay, so it's the set of pairs. So I'm going to write it like this. So it's a set of pairs. So an element of the symmetric product, just like in Martin's talk, I'm going to describe through an effective divisor on sigma. Okay, of degree D. So I'm going to call it D, and then a point on Y on sigma, which I call Y. Remember that I was playing with the base being sigma, and I'm sorry, Y, and that's why I call it usually like this. So X for me is, unlike in Oscar's talk, is the target, not the domain, not the base of the bundles. Okay, so it's the set of pairs such that the support of the divisor contains the point. Okay. And now this is the, so if you know algebraic geometry, you know that this already gives you a line bundle over this compact complex manifold, which I'm going to call so there's going to be here a line bundle, which I'm going to call PD. Okay, so this is going to be a line bundle. Okay. So so this phi is going to be a section of this line bundle. Okay. Before we get to the section, okay, so this discriminant locus or discriminant divisor or universal divisor, okay? So I want to have this, so this D being the set of, so it's going to be where this section vanishes, okay? So in a way you are sort of gluing together all the vortices, okay? So when you fix these, right, you want to think of this phi as like the corresponding phi, okay? So this vanishes certainly on the, yeah, so basically you get the divisor there, right? So this makes sense, okay? So, but before I tell you more, I give a more precise formula for this phi, let me just say that, so here we have only this line bundle, so it's called the universal line bundle. Okay, it is just a complex line bundle. It does not have any metric structure. However, there's another construction to obtain PD, which is like this. So you take these space of vortex solutions in degree D. These are already in my notes for in the previous lecture. Okay. Okay. So you multiply by the line bundle. So remember that we are fixing a line bundle. With the bar means that we are fixing a Hermitian structure, okay? So basically, so there's an action of the gauge group in both of these factors. So I can take the quotient, and you can, and you can, it's not hard to check that this is actually giving the same object, okay? So the advantage of this description is that, so this is an isomorphism as, a bundle over that complex manifold, as I mentioned, D+1. But actually, I can use the isomorphism to transfer the metric structure from L to here. Okay, so now I use this map, or actually I would say this map to pull back the metric structure. So now it becomes PD with the bar. Okay, the bar I recall means that there is this. So it's not just complex geometric. There's also this metric structure. Okay. Okay, so this is a good way of describing these universal objects. So think of let's start with this phi. Okay, so let's just look at this map. Okay, from this product to this product that you get by so this is just a solution of the vortex equations with the right degree, okay? And now a point in sigma, right? I'm going to associate, that with now, okay? So this makes sense. And then there's an equivariant map for this gauge group action. So you can look at the quotient. So the orbit to orbit, there's a map that makes sense, okay? So that map is phi. Okay, so just go, so do this thing. Now you just divide, so both sides divide by a G action. And then you get this phi, okay? So now this dA, this dA is just the chain connection of PD with the metric structure. So Oscar already used this notion of chain connection. He explained in a sentence, okay? So no one complained about chain connection. So I know that you already know everything about the chain connection. Okay, so this is how you do it. Okay, and now the main result. Okay, and now this is where the fiber integration. So I'm going to tell you how to look at this L2 metric. Okay, this scalar structure. Again, the complex structure is easy. Now we need to describe either the Riemannian structure or the symplectic form. Okay, and here's the formula. Okay, so so there's some factor, and then it's an integration of. So basically, I'm using the projection to the other factor. Okay, and the fiber of that map is sigma. So I'm integrating over the fiber. So each time I'm integrating over each point of the moduli space, I'm integrating over sigma. So now I have here some form which is going to be of degree 1 plus 2, yeah, to get something, some differential form of degree 2. That's what you expect. Let me tell you what this is. It's just tau. So tau is the tau that appeared in the vortex equations, okay? Tau, and then I pull back the symplectic form on sigma, okay? I wedge it with the curvature of this chain connection, okay? And now it's the square of the curvature. So this is the formula, okay? So I'm not going to prove this. I'm going to maybe say, I say, so this is the Timperutz. There's a Biswas, Schumacher. There's also Batista. You should write the name here also. So they explain why this works. Okay, so I'm going to use this because I'm going to use it later. I'm going to put here an asterisk to refer back to it later. Okay, so this is the, an alternative point of view to what you heard this morning. And this is actually, so I'm doing this now for the, in the compact case, unlike Martin, who was explaining these in coordinates, right? He was working very hard. He almost got the formula right for this localization, okay? Right, so now we go, so this lecture, I'm going to assume a little bit more about your background in algebraic geometry. I have already done that, a bit of geometry, but I don't really have to, I don't think I should get all the details, late as I go. So some statements, you might think that, you don't understand really what's going on, but you have to make sure that you really understand at least the meaning of what I say. And I'm available to explain more and also to point out where to read more, like a proof, a written out proof of everything, okay? So the next, so the third description that I'm going to give uses, so using let's say, so index bundles and Arakelov geometry. Let's say, well, so let's say, so Arakelov geometry. Arakelov geometry is some kind of branch of algebraic geometry that uses also these metric structures, not only complex geometry, but also the, so L2 metrics and things like that. Okay, topology also, So, so the main concept here, the main tool is this, so let's say the link pairings. Okay. Okay. So this is basically the main result that I'm going to present here. It's just actually, it's, what I promise is to do the geometric quantization of these Keller structures. So I'm actually doing a bit more. I'm going to explain, really how to get the quantization in the sense of geometric quantization. So in order to compute let's say the L2 metric, you just take the curvature of the relevant connections. So I'm doing even more than explaining how to get the L2 geometry through using these tools. Okay? Right. So now there's going to be a technical interlude where I explain a little bit without too much details because I don't have time. So Quillen's metrics, so Quillen's metric and the link pairings. Okay, so by the way, so for this kind of technology, I think a very good resource now are the lectures by Jean-Michel Bismuth in the previous meeting on vortices that are organized in August. So we invited him to give a mini course about all this stuff, not necessarily referring to vortices, but the main formulas that I'm going to use. You can understand them better in this context of the whole theory that he explained very well. So there's some slides of his lecture that are sort of easy to follow. And you can also watch on YouTube the actual lectures that he gave. They are accessible. So I recommend that as a background to what you're just hearing now. So you should have done that maybe yesterday. I don't know. But no, I mean, this is actually, it's very good, very good lecture. So I start with the following definition, which looks like very naive, but this is really everything. It's the main stage of where everything is going to be placed. So it's a family of curves. Family of curves. Okay, so a family of curves. So it's a map. Like so, it's a map between complex manifolds. So usually I write this like this. So this is the total space, and this is the base. Okay, so this is a submersive holomorphic map of quasi-projective varieties. Well, let's say, sorry, manifolds. It's a manifolds. Okay, so with connected fibers. Of dimension 1. So the dimension, so I take for every point little s, I look at the fiber, and this is of them. It's a Riemann surface. Okay, the complex dimension is 1. Okay. So I'm continuing so definitions. The relative divisor. Okay, so it's a divisor in okay, C, such that you get divisors by restricted to each fiber. So D intersected with each fiber is some let's say ds, which is a divisor in the corresponding fiber. Okay, for all s. Okay. The main example is the canonical. So the relative canonical divisor. So relative canonical. So okay, so this is so it's the canonical divisor of C, but then I do this thing. I just tensor with the pullback of the canonical divisor on the anti-canonical divisor on the fiber. On the base, sorry, on the base. Okay. And now all of these, we are in the realm of Arakailov geometry. So when you fix now a metric structure, so this is what I'm going to say that so I can put here bars on everything. Okay. And then I can deal with these things that Chern, unitary connections, Chern connections, all of that. Okay. Okay. So now equivalent metrics. So this is a metric on a line bundle called a very important line bundle called the determinant of cohomology. Okay. So let's just. This means that there is metric structure. For example, I have. So often we will need, for example, a Kähler metric on S, for example. And the Kähler metric on S means there's a metric on the anti-canonical bundle. So this is okay. So so the determinant of cohomology. So given given a holomorphic vector bundle E on C. Okay, so we start with a vector bundle upstairs. Okay, and now we cook something which is actually in the base. So the determinant of cohomology is going to live in the base. Okay, so the determinant of cohomology of the family of curves is the line bundle on S. Okay, with fibers. I'm going to say each fiber is going to be a vector space. It's going to be actually a complex line. Okay, so the complex line So this is how I'm going to write lambda of E, it's the determinant of cohomology of E, okay? At S, okay? So this is, so it's the, I look at these vector spaces, which are the cohomology, so I'm looking at this, the cohomology groups. So if you want, I mean, I can, this is shift cohomology. I can interpret these also as, Dolbeau, whatever you are more familiar with, the algebraic or complex analytic. Okay, so this is, so these are lines. So these factors are lines. Okay. Okay, and now I take here the dual. Okay. Okay, so these are just like lines. You have a line for each point of the base, but the point is that you can glue that together to get a vector bundle all over S. Okay, so this is the Knudsen-Mumford. So these lines, these complex lines, glue together. Okay. Anyway. Okay, so up to now, this is just a line bundle. And now I'm going to give it a metric. Okay, so now if I'm going to write like this, so if E bar, Sushmita, this means that if E, the vector bundle E, is given a Hermitian metric, okay? Okay, then lambda of E receives a very natural. So at the moment, so when you look at it, when you look at the definition, it looks something horrible. Why are people even interested? Why did this guy just write this on the board? But the thing is that this line bundle is a miracle. It's a miracle, and it, for example, appears in problems in physics, and it allows you to do things non-trivial, for example, describing metric. Okay. So receives a Quillen metric. So this is the definition that I'm going to give. So I call it usually HQ. Okay, so the note. So let me explain how this works. So the note by so HL2. Okay, the L2 metric on harmonic representatives. Okay, on these fibers, yeah, and then okay, and then so if you like, so you're dealing here with, like, let's say double cohomology, right? And we know that by Hodge theory you can represent the classes by harmonic sections of E, right? Okay, and this is basically what and then because you have the L2 metric that works for any section, I'm taking particular sections which are harmonic. Okay, and now I'm just going to say, well, okay, so now we have this metric, which gives you an inner product for each S. Okay, and now I'm going to define the zeta function of the Dolbeau Laplacian. Okay, so this is a formula like this. So this, I take the, okay, so I look at the spectrum, the positive spectrum of these operator, the double Laplacian. Okay, I look at the positive spectrum. Okay, and I just do, I can define by the eigenvalues to some power t. Okay, so t here is a complex number. So this is the spectral zeta function. And then you can prove that for a t with real part that is large enough, okay, this converges, and then you can analytically continue back to 0. Okay, so this can be analytically continued to t equals 0. Okay. Yeah. So again, so this is the Laplacian. I use the Delbar operator. I use the adjoint in the L2 metric. Yeah. Yeah. Okay. And now the Quillen metric. So the Quillen metric is given by this formula. Don't complain because I already told you it looks strange. So exponential of the derivative of this analytic function at 0. Okay, so exponential of that multiplying, so it's a factor of the L2 metric. Okay, yeah. Okay, so I'm just saying that the formula looks a bit strange, but this is somehow it's going to solve many problems. Okay, so now the link pairing. So given, okay, so to get the determinant of cohomology, you need a vector bundle on this total space. So here, to get to define the link pairing, I need 2 line bundles on the total space. So given line bundles L and M on C, okay, so they're the link pairing. Okay, is so LM. So it's again, it's going to be a line bundle on the base, okay, which I'm going to write in terms of determinants of cohomology. Okay, so line bundle is a vector. It's an example of E. Okay, and also the tensor product. So this is what it is. So I take the tensor product, and now I sort of divide by L. Oops, divide by the determinant of L. So here, this is the dual. Okay, an M, okay, and I add a correction term. Okay, so this is the structure sheaf of C, okay, which is if you like, the trivial bundle also is a vector bundle. Yeah, okay, so it's going to be a bundle on S. Okay, so now, because this is, so now the point is that all the factors have determinants of cohomology. So I can also take the kind of product of determinants of cohomology. Okay, so this has, so let's call it again, the Quillen metric. Okay, so this has Quillen metric. Okay, metric induced by the Quillen metrics of all of these. Okay, so Sushmita, L bar and M bar, okay? When you have these, when you are in presence of these structures, okay? Okay, so now let's go to the wonderful properties. Okay, so the first one is that, you can take you look at, you can take the first Chern class. There's a formula for the first Chern class, which is the following. It's a formula by fiber integration. Okay, so it's it looks like this. It's just the product of first Chern classes integrated over the fiber. Okay. Okay. So now the property. So if you have an isomorphism of line bundles, so complex line bundles, you have also the you have that for every other line bundle. You have, so LM is going to be isomorphic to L prime M. Okay, so the pairings are going to be isomorphic, and this also works with the metric metric structure. So the point is that this is not going to be an isomorphism with the metrics. Okay, this is isomorphism of complex line bundles. Okay, not of, so the metrics, it won't be an isometry. So not an isometry. So not isometry. But there is, I'm not going to write it down. There is an explicit formula relating the two metrics. Okay. Well, anyway, so now I'm going to state the main theorem that is necessary to the magic that I'm going to perform when I erase the boards and amaze you with the holomorphic quantization of vortices. Okay, so it's packed in this theorem, which is due to the lean. Okay, sometimes people call it the Riemann-Roch isomorphism. Okay, so okay, so for yeah, so now you have the line bundle. Okay, so there is a canonical. So there is a canonical isomorphism. Okay, so this is the statement. This is not trivial to show at all. But the formula is nice. It's just yeah, it uses this relative canonical bundle, actually the anti-canonical bundle. Okay. And now the thing that is really important is that this induces an isometry of Quillian metrics. Okay. So this is very general. It's very hard to prove. We're not going to use it as it is. We're going to use a corollary, which I think in the original proof of the link, this was actually a lemma to prove theorem. Okay, but this is so it's something that happens in a special case where you are dealing with the killer metric on the base. Okay, so yeah, so now we have a line bundle C, but now with the metric structure. Okay, so metric structure C, and now in the case that we are interested in, so it's this kind of thing. It's the product. So C is the product of the base with the fixed Riemann surface. Okay, and now we have that the base is scalar. Okay, so there is this, yeah, so now this is the formula that is really, really important in this talk. So the first class of this line bundle, this attempt of cohomology, it's equipped with the Quillian metric, okay? And now I'm going to give a formula for this in terms of just, yeah, so the metric on the fiber, and yeah, and the first class of L. So it's going to be like this. Again, going to be a fiber integration formula. Okay. So something that I should say is that when I said that I'm going to look at different ways of describing the L2 metric, all of them are related. So it's very important to realize this. You know, all of them are related. Okay, so here we already see a fiber integration formula. That's well, anyway. So so this is how it is. So it's the So yeah, so it's that, and now we have these things. So so here I'm pulling back the Ricci form of omega sigma. Okay, so people that are familiar, that know a bit about Quillian geometry, they have met the Ricci form. So the Ricci form is such that, so you have a metric, you have the Ricci form, the Ricci tensor, right? You can construct interpret it as a two form which has the property in Quillian geometry that the cohomology class is independent of which Quillian metric you use to compute it. Yeah. Okay. So this is basically the main thing. The main theorem that the main result is basically this formula here that I'm going to use. Okay. So I'm going to use these, of course, for the case where we have the second projection, the projection to the base. Not the one that I call P at the end of the long boards, right? But P appears here. Yeah, okay. And yeah, and then I'm going to do this with the case where certainly the base is scalar with this omega, this omega L2. Okay. And I'm going to use this also I'm going to take L to be this universal bundle PD that appeared in the sort of viewpoint 2. Okay, so let me just here now do some. I'm not, my course, I'm not going to do many calculations, but let me just do here a very precise calculation. Okay, so I'm going to say, well, this is what. So using these, you can write a formula for omega L2 like this. So first of all, I'm going to use the formula asterisk from the end of the board. Okay, I'm going to use this formula that appeared in these papers by Tim Perutz and so on. Okay, so I'm going to, I'm going to use this, so I'm going to rewrite this like this. So it's integral the sigma C1 of PD, okay, wedge C1 of PD minus tau, now the pullback of omega to pi. I think the factors are like this. Okay, so let's see, yeah, okay. So now I'm going to do, one of these very useful mathematical tricks, very powerful mathematical tricks, which consists of taking some formula which looks very complicated, then we subtract something and add the same thing. Okay. So it's something which is really, almost, yeah. So you see that I'm going to write C1. This thing is I'm going to call C1. Okay. So C1 plus 1 over 2 pi. Rick. So I'm going to make this term of the Ricci form appear. But now if I make it appear, I have to make it now disappear. Okay. There. Does this make sense? Yeah. Okay. And now I'm using here this corollary. Okay. And I'm going to write this like this. I'm going to say that this is just C1 of lambda of PD minus 1 plus. So this is, in a way, I'm using something just completely obvious to rewrite the formula in this was Perutz and company in a way which is which I know it's true because of these these techniques of playing with the determinants of cohomology. Okay, this is a plus. Yeah. Okay, so because I'm also going to use this later, I'm going to call this star, but the sort of more sophisticated star. Okay. Okay. So I think at this point, maybe you have some questions, or you want to repeat something, or no? Okay. Okay. So now I'm going to erase, and I'm going to explain how to do this geometric condensation. Okay, so Kähler quantization of vortices. Again, it's the calculation of the modular space in the sense of, so it's just geometric quantization. So the aim, I'm not going to write it down, is just, we're doing geometric quantization of the phase space, which is the modular space of vortices. I'm just dealing with this case of line bundles. It's a phase space with the symplectic structure given by omega L2. Okay? And now I'm going to use the natural Kähler polarization. So because all these spaces have a complex structure, so I'm going to use this complex structure to define a polarization. So I'm not sure if, so let's see how I'm going here. Yeah, this is not looking so good, but okay, so just maybe quickly. So geometric quantization. Okay, so just very quickly. So is everyone familiar with geometric quantization? No, maybe I think I. So in general, when you have a symplectic manifold, okay. So what is geometric quantization? So it's a construction that allows you to do quantum mechanics more generally. So you need to first construct what people call a pre-quantization of the symplectic manifold. Okay, so pre-quantization. Okay, so this would be Hermitian line bundle. So it's going to be, well, let's write like this. Okay, with the unitary connection satisfying so this is the most important equation in geometric quantization. We want the curvature of this connection to be just proportional to the symplectic form. Okay, so there is this constant here which is fixed. So I'm going to say mostly that this h bar equals 1, but usually you do So there's going to be one parameter family of these constructions. Yeah. Okay. So this is what, yeah. So pre-quantizing means constructing such a Hermitian, so a line bundle with a metric that you need to construct in some way, and with this property. Okay. So given these, we have a pre-quantum Hilbert space, okay, which is the space of sections of this bundle, okay, which are L2, okay. So there's a metric. So maybe here you want to use the, yeah. So of course so when you're doing this with the Keller manifold, you want to use the Keller metric and so on, okay. So you have in principle an L2, yeah. So most of the problems you're tackling, there's a way of defining an L2 form, and then it's Hilbert space with respect to, let's say, an L2 metric. So you want to look at the sections that have finite L2 norm. Yeah. Okay. And now this is the idea, so which not always works. So you have, so to each smooth function, you want to now associate an operator in this Hilbert space. So the cheapest guess is to say that, well, I'm going to do the following. I'm going to do the, so let me just write here the formula with, yeah. Okay, so this is the Hamiltonian vector field of the function. I think I called it like that, the other, okay? Okay, so so I can, so this is sort of almost does the, what we want the quantization to behave, you know, but not everything, okay? And now this actually is not really quantum mechanics, because in quantum mechanics, so phase space is like treating the p's and the q's, and we want the way functions depend either on the p's or either on the q's or a combination of them, but only on half of the degrees of freedom, okay? So we need to cut in half the degrees of freedom. So this is done by a polarization. So we have to polarize the wave functions, okay, the pre-quantum wave functions, okay? So polarizing, so it's a gadget that, you know, polarization P is a gadget that does this thing. So the, okay, so when M has a complex structure, okay, then, so let's see. So when there is a complex structure, there is, yeah, the way you polarize is to say that you want to deal with the, for example, holomorphic sections. Okay, so this means that psi is PJ polarized if the size are covariantly constant for anti-holomorphic. So the T1J, yeah. So here I'm using I'm using J to say what are anti-holomorphic vector fields. Okay. Another, yeah. So and then the polarized section. So it's the intersection of this L2 property with this holomorphicity property. Okay. The L2 property is trivial when we're doing, for example, with them compact, and then you're doing basically complex geometry. Yeah. Which is the case that we're interested in, okay? An observation is that, yeah, in general, you won't get automatically, you know, in this way, something that will act on this space, you know, the polarized part of the Hilbert space, because these operators act on H, but they might not give, you know, they not leave this space invariant, okay? Okay, so there is also this question of Hitchin connection. So sometimes people worry that, yeah, here there are choices, but then in the quantization, you don't want your construction depend on choices. So there's a way of proving that very often, choosing different complex structures that are compatible with the symplectic structure. It doesn't matter, because you can parallel transport one to the other. And the most general way to do this is using a projective-verified connection that will still identify not the Hilbert space, but the projective space is associated to the complex Hilbert space. So this is called the Hitchin connection. It's a tool that is used in many contexts, but especially in this context of proving that there is no dependence on the choice of holomorphic polarization. Okay, so Hitchin connections, just independence of J. We're not really worried about that because we have a natural J that we don't want to move. Okay. And then the other thing that I want to say is so metaplectic correction. Okay. So this is, so I told you that usually you have already maybe symmetric structure here, and then you can talk about the altometric, but sometimes not. And one way of going, solving this problem is to work with not just functions, so sections, but you tensor by, so it's, so you look at a more sophisticated Hilbert space. So instead of looking at holomorphic sections, you look at holomorphic sections now, tensored by, a form of degree half the dimension of your base, okay? Because then when you multiply two of them, you get a form of top degree that you can integrate over the base without needing any more geometry, okay? So this means that, so here, so this is the case of, we are dealing with, in this case of complex polarizations. So this is a choice of square root of canonical bundle for a choice of, complex structure, okay? So this is like a corrected Hilbert, metaplectically corrected Hilbert space that sometimes will get you different answers. So this is just not only a technical thing to solve this technical problem, some way of using this, solving the technical problem, but the answer is going to be different, and sometimes the answer is going to be better than what you think. You try to solve a problem, but then actually you solve many other problems that maybe you had not thought about. Okay? But this is somehow an optional thing. It's like a more sophisticated sort of second order. You're doing a more perfect geometric quantization of your problem. Anyway, so now I want to explain how to do this. So this is not the most general context for geometric quantization. This is just this kind of one board, two board explanation of what is geometric quantization. It's just, in the case of complex polarizations, which is the only one that I need right now. I'm already in 10 minutes. Okay. So now this is, okay. So this is a bit embarrassing, but okay. Okay, let me state the theorem at least. Okay, let me state the theorem. Okay, so assume, two, this was for one, so for two, okay? So geometric quantization for vortices. Okay, so now, so assume that, we have, this quantization of the volume form on sigma. Okay, by the way, one thing that I forgot to say. So this equation here, it basically says that, well, if you have a varying family of omegas, you should not expect this to be true for the whole family, right? Because we know that when you take homology classes, right, you have the homology class of omega would be a multiple of some integer class, right? Okay. So here, this is this kind. So this is there is this kind, usually this kind of assumption. You cannot just quantize anything here because this equation here will impose you a quantization called the Veil quantization of omega, and this is basically the assumption that I'm doing here. So I make an assumption which is just enough to ensure that I can pre-quantize sigma, not the modular space. Okay, sigma. Okay. So it means that that thing here will, for choice of tau, that equation will make sense. Okay. And now we define. Okay, so if it makes sense, we can find a pre-quantization of sigma itself. Okay, so pre-quantization. Well, actually, this is a pre-quantization of tau over 2 omega sigma, okay? So now I define M bar, which is, so the pre-quantization, and now I sort of twist it by this kind of anti-spinor, okay? Yeah, because this is now a line bundle. Okay, I'm using here the metric structure from the calorimetric there, right? And I'm saying that, well, now I'm going to say, so this is a line bundle which has curvature. So this has curvature. So 1/2 the Ricci plus tau omega. Okay, so theorem. So this is something that it's in a paper with by Ericsson and me. Okay. So the line bundle. So I'm going to give you basically the recipe to quantize to do these geometric quantization vibes. Okay. So the line bundle LM. Okay. So M is this M here. Okay. So given M. Okay. To define M, we just new Q. Which you just need Q, which is basically the pre-quantization of the surface again of the surface. Okay. So the line bundle, so now I'm going to write you the formula. So I'm going to use now this technology that I told you about, colorimetrics, the link pairings. Okay. On SD sigma, okay, provides a pre-quantization of omega L2. Conversely, all Keller quantizations of the modular space of vortices arise in this way. Well, so here I have, so this is a Keller manifold with this data, so arise in this way. Okay. I think I'll just stop there.